Okay guys, I promise this did go really well about 2 minutes ago, then the cleaner came in, so this is a replay. It's going to be crap now, I know it. Righto, so relating forces and momentum together is reasonably simple, I hope. So if we have an object like this thing here and we want to change its momentum, remembering that momentum is a property, momentum's a vector, because mass isn't, but velocity is a vector. Something with momentum has both mass and velocity. If we're relating forces and momentum together, this is kind of what we need to start with. So if we want to change something's velocity, we need to make it so a change in velocity is going to cause some sort of acceleration. That's an arrow because it's a vector. If we've got some sort of acceleration, we need some sort of force to apply that force, I guess, to change its, to give it an acceleration, to change its velocity, to therefore change its momentum. So if we don't have any forces, here's an object, here's a force, here's another force. We don't have any net force on this object, so that thing's not going to change its momentum at all. You're watching this video, I went through this story before and it was heaps funnier. You're watching your video, you're sitting on a chair, you're laying in bed, you're sitting at the kitchen table, whatever it is, and you might have been just over there in the classroom. Gravity's pushing down on you, that's a force. Your chair is pushing back up, that's applying another force. So there are two forces on you, but you're considered to have no net force on you in isolation, no net forces, no change in momentum. So you're going to sit there until the bell goes, or so you think it's time to pack up, or something else comes on YouTube and you get up and get something to eat or something, I don't know. So in order to change the momentum, we need to change the velocity or change the mass. That doesn't really happen for specific objects yet. I'll get to it. By creating some sort of acceleration by applying some sort of force. That's better. Right, so impulse force, F equals the change in momentum. Force equals change in momentum over some time interval. If we want to look at the change in momentum, so we're going to go F equals ma, because F is always ma, that's Newton's second. If we apply some force to a mass, we will make it accelerate. If we make something accelerate, what we're really doing is changing its velocity over some time interval. If we look at the top line of that, P equals mv, it kind of looks now a little bit familiar. So we've got some sort of force will change something's momentum, m delta v, over some length of time. Think of it like the brake pedal in your car, the brake pedal in a B-double driving down poor road. We want some sort of external force, some sort of net force to apply, to be applied to this mass to change the momentum over some sort of time interval. If we make that force bigger, we make the change in momentum bigger, so something slows down quicker, which is really good, especially with grain trucks and stuff like that on the road. If we want to look at how big this change in momentum is, we can do that vectorially, so or using vectors. What we're looking for is to find out if there is some sort of change. You'll look at a whole bunch of stuff. There's going to be stroboscope type images of pucks on an air-hockey table, cars in an icy intersection, I don't know, kids going ice skating or something like that, and it'll be, here's the initial momentum, here's the final momentum, was momentum conserved in this system, yes or no, and the only way to really find that out is to draw some vectors. So we're going to draw some vectors. There's a vector, and let's go yellow, and there's a vector. I've just made these up, so if momentum is conserved, I don't know, P1, PI, we'll call that because it's the initial, and we'll call this PF because that can be our final. So in order to find out change in momentum, we want the final momentum take the initial momentum. That's how you work out if something's changed. You get what it finishes at, take away what it started with, and you know how much did 2 change turning into 10. 10 take 2 is 8. That's how much it changed. So now we have these two things here. What I'm going to do now is, using the magic of rubbing things out and redrawing them, what I'm going to do is pick this vector up here and somehow stick it on the end of this one. And I've just worked out a problem that I've written this here too close. Let's take that away. And I'll rewrite it down the bottom. And it might look like I'm rubbing this out right-handed, but I'm actually rubbing this out left-handed. I'm not very coordinated left-handed when rubbing things out. Change in momentum is final momentum, take initial momentum. here's my final. I'm going to take the initial. This is also equal to that, right? So what I'm going to do is add the negative of my initial momentum. The negative of my initial momentum is longer. That's about right. That's the same size, same magnitude as my initial momentum. Now it's opposite. Alright, so now what I've done is final take initial. So I'm adding the negative. Makes life a lot easier doing it that way. Now my change in momentum is that. And from careful observation, you can probably see that that doesn't equal 0. So in this case here, it's not 0, not conserved. Okay, so if the change in momentum is not 0, it's not. Momentum is not conserved. In a lot of the instances that you'll see this section, it will be. Alright, now if we want to use this guy over here and another system, so we've got two objects colliding with each other, what we can start doing is putting things together using Newton's third law. So Newton's third law says that we have, wow, that's terrible. If we have, sorry about this, if we have an object that is applying a force on another object, there's an equal and opposite force back on the initial object. So the force from the first one is equal and opposite to the force from the second one. So if I have my two fingertips pushing against each other, one is pushing to the left, one is pushing to the right. You guys can work out which one, but it's the opposite for me anyway, so let's not worry about it. We've got this scenario. What that means is that the force here for the first one is equal and opposite to the force for the second one. So now what we can look at is change the momentum of the first one is equal to the negative of the change in momentum of the second one. Now hopefully you've worked out that if one finger is pushing on the other one for a certain length of time, it's pushing back for the same amount of time. So the numbers down the bottom are the same. So change in time for both of these, for this interaction, is identical. So I guess they can kind of cancel out. Pretty useful. So now what we've got is this system of two particles, P1, P2, or object 1, object 2. So there we go, object 1, object 2, finger 1, finger 2. So we've got this system where we've got two particles interacting with each other. So it's that, or so delta P1 is equal and opposite to change of momentum of P2. Change of momentum 1 plus change of momentum of the second particle is nothing. So what we've got in an isolated system, no external forces, so nothing other than this force, which is the collision force, the change of momentum of the first particle plus the change of momentum of the second particle, and if we have up to billions and billions of particles, change of momentum of the third and fourth and fifth and sixth and seventh and blah blah blah, no external forces, only internal interactions, we have no change of momentum, or momentum is conserved, unlike this scenario down the bottom here. Alright? This is going to look weird, but I'm just going to do it like my adorable niece Emily would draw a rocket, and this is a rocket. So here's our rocket, and Elon Musk is really proud of this technology. He's going to launch this thing to Mars with his car on the bonnet of it. On the front. No, I'm not going to draw a car in there because that'll make me look silly. So here's Elon Musk, he's launching his rocket up, and what he's looking at is the change of momentum of the first thing, his rocket, versus the change of momentum of, let's get some colour, the second thing, which is the rocket fuel. Alright, so if he can get the one of these things to go downwards, the other one will go upwards, equal and opposite forces, equal and opposite momentums, all that sort of stuff. So if he can get enough fuel to come out the bottom of this thing, it'll actually make the other thing go up, overcome gravity, all that sort of carry on. So that's exactly what happens. He makes some stuff have momentum downwards, gives his rocket momentum upwards. The cool thing about this is the size of the change of momentum down here is constant, but the mass of this thing is not. if we're spewing a whole bunch of rocket fuel out the bottom of this thing, its mass is actually getting less because it did have that inside of it. So this mass actually goes downwards. So this acceleration goes upwards. So there's a constant force going out the back end of this rocket, but it's actually accelerating upwards. It's not just going upwards against gravity, flying, whatever. It's actually going upwards faster and faster and faster and faster, and its rate of increase of speed is faster because it's accelerating more and more and more the whole time, and it's really, really cool. All right. So in this section, you will be drawing diagrams to do with objects that are going to undergo collisions. You will have a certain amount of momentum at the start, and you will have a certain amount of momentum at the end. And what you will identify is if momentum is conserved in this situation. We have a vector that's going to represent our initial momentum. We have a vector that's going to represent our final momentum. And we're going to add those two things together. So momentum 1, momentum 2. We're not finding the change anymore. We're doing vector addition. So if I get those two things and stick them together, I'll pick this one up. I'll pick this one up and put it on top of that one. About there-ish. So my overall vector, this is getting ugly. That is my PI. Alright, if I look at my final momentum, it's going to get horrid. That's the final momentum for that particle, my yellow. Here's the final momentum for this particle, so I get this one and add it to this guy, or the other way around. Order's not important. 2 plus 3 is 3 plus 2. As long as you put the right things in the right spot, you're good. So here we have that one plus that one. So now, well, that wasn't too bad. That is my final momentum. So I've added the final bits of momentum together, the initial bits of momentum together. I've got this thing here, I've got this thing here. Those lines are not the same distance, they're not parallel, not conserved whatsoever. The only way the only reason this can be considered to be conserved is if this thing and this thing, so this line and this line are the same length. Clearly they're not, and also if they were parallel to each other, because that would mean that they're same size, same magnitude, the same length, and same direction, because they're parallel. Alright, and that would mean they are the same vector, which would mean that there's not been any change in them. So that would mean no, no accelerations, because no forces, conserved because it's in isolation. Okay, yeah, I reckon that'll do us for today.